Improper integrals are useful tools for investigating series. And what is an improper integral? An improper integral is an integral of the form uh, you have some bound a up to infinity for the upper bound. And first of all, let's draw a picture of what this is meant to represent. You've got, and we'll assume that our function here is non-negative. So it's greater than or equal to 0. So let's draw a picture of such a non-negative function. Maybe it looks something like that. And we want the integral from a to infinity. And the intuition there is that a is some finite real number. Maybe it's right here. Here's a. And remember, integrals, definite integrals, represent area under the curve. When the curve is non-negative, it's simply the area underneath this curve. And we want it from a all the way out to infinity. And because this particular function is shrinking down to nothing, it's not entirely clear whether, if we go out to infinity, if this would be a finite area or an infinite area. And like anything else, this is all about taking a limit. And that's the definition of an improper integral. If we can't, infinity is not a real number, so we can't actually integrate and plug it in, but we can integrate, plug in a b, and then take the limit of that as b goes to infinity. So if lowercase f has an antiderivative of capital F, you would end up with the limit as b goes to infinity, capital F of b minus f of a. All right, and back down here in the picture, what does that mean? Well, the b says that we're going to just take some b value right here, and we're only going to take care of this much area. All right, but then we're going to increase our b out to infinity and get more and more area until, if we limit it out to infinity, we would eventually envelop all of it. Okay, so there is our definition. Just like series, we have a notion of convergent and divergent improper integrals, and it simply means it's convergent if the limit exists, and it's divergent if the limit does not exist. All right, just like for series, are convergent when the sequence limit exists, the partial sum sequence limit exists, and divergence if it does not. Okay, let's take a look at an example. So here we have an improper integral. Does it converge or diverge? If it converges, what is its value? So let's take a look at what that would evaluate to. First of all, the picture does not help solve this problem, but I can draw it anyway. This is like y equals 1 over x squared. It looks a lot like y equals 1 over x, but it shrinks a little bit quicker because it's a square. And we want from 1 out to infinity, and so what we're looking for is this area right here. And I'm drawing this freehand. It's hard to tell how quickly this shrinks. It does limit to 0. You can tell that as x goes to infinity, the value of y, if y is equal to 1 over x squared, limits to 0. So the question is, does it pinch down hard enough, fast enough, so that it cuts off all the area? So let's see. Let's find out. So what we're basically doing, here's the part that we actually do need to do, is replace the very first step. As soon as you have that infinity up here, replace it with a b. So the limit from 1 to b of, and I can write that as x to the negative 2. That'll be easier to integrate. And I have to do that first step, changing the infinity to a b, because I can't plug in infinity. That doesn't make any sense. So let's let's take a look. If I integrate x to the negative 2, I increase the power by 1. I multiply by the multiplicative inverse from 1 to b. Still got to take the limit as b goes to infinity. And then 1 over 1, of course, is nothing. It's just negative 1 over x. That gets me negative 1 over b when I plug in the top, minus a negative 1 over 1 when I plug in the bottom. And of course, the limit as b goes to infinity of 1 over b, that's 0, which tells me that this area right here that I drew in the parentheses is in fact 1. And you can tell that even though it stretches out infinitely far to the right, maybe it gets so short so quickly. I did this freehand, so it's hard to tell, but it would get so tiny as we go out to infinity that it's basically nothing out here. And that's why the whole area of this is the same as the area of the 1 by 1 square here. All right, and of course, since I got a number, the limit exists, so I say that the integral converges. All right, let's take a look at another. All right, similar sort of question. Does it converge or diverge? If it converges, we should be able to compute the value. And the picture is actually very similar as well. Again, I'm doing this freehand for you. But 1/2 root y, that root y, as we go out to infinity, that's going to go, here we have, let's say that's the y-axis, and this is the z-axis maybe. So I'm drawing z equals 1 over 2 root y. If you don't like that, just change all your y's to x's, and that'll work the same way. Anyway, so we've got z equals 1/2 1 over root y, and that would look very similar. But it wouldn't go to 0 quite as quickly. It does go to 0, but not as quickly. And we go out 1, 2, 3, 4 here. So I'm looking for this area right here. And this will pinch down to 0. It will go to nothing eventually, but it will do it more slowly than the squared term. And maybe that'll make the difference. That'll make this area infinite. And we'll confirm that by actually computing it. So I'll go down here and get the limit. It's always the first step is replacing the infinity with the real number b, which will limit to infinity. And I'll write this as 1/2 x to the negative 1/2. I should do y, shouldn't I? All right. And so I'll increase the power by 1. So 1/2, negative 1/2 becomes positive 1/2. I'll divide by positive 1/2. Oh, and that cancels out all this. And that makes sense because if I take the derivative of y to the positive 1/2, the 1/2 comes down, 1/2 becomes negative 1/2. So that is the derivative of y to the 1/2. I've got 4 up to b. Limit as b goes to infinity. And so what do I got? I've got the limit as b goes to infinity of, let's see, 1/2 power of b, that's the square root of b, minus, I don't need a limit anymore because I'm just plugging 4. 4 to the 1/2, the square root of 4 is 2. But here's the thing, this bottom doesn't really matter here. All that really matters is if the limit as b goes to infinity, the square root of b, that diverges. That diverges to infinity because you could take the square root function as b goes out to infinity, the values are going up to infinity. This will increase forever. All right, so definitely this is a divergent limit here, which means that this area that I drew up here in parentheses, while it gets, it does eventually close up out towards infinity, but not fast enough. There's still infinitely much area going on here. So that's definitely going to be a divergent area. We can't compute it because it's infinite, basically. All right, there's another type of improper integral that we'll need to be familiar with, although this won't help as much for series. It's useful in general. and it's when an integrand is undefined at an endpoint. And so I'll just go ahead and do the example. All right, we're going to find the value of 0 to 8, z to the negative 1/3 dz. And so we'll draw a picture of this. We don't have to draw a picture, of course, but again, we have, let's say that's, here's the z-axis and here's the y-axis, and we're graphing y is equal to, I could write that as 1 over the cube root of z. That's the same thing, right? And this, again, looks very similar to the pictures we've been drawing. But what I want is the area from 0 to 8. And let me draw that, fill that in with a different color maybe. So I want to know what this area is. And it's very tempting to just do this like a normal integral, but the problem is this 0 right here. This 0 is not defined. If you tried to plug that in, you get 1 over 0, and that's not a real number. That's nonsense. I have to scratch that out immediately. I'm embarrassed for even writing it, right? That doesn't make any sense. But we could still treat this as an improper integral. Improper integral basically means that, just like if we have infinity in a bound, we can't plug in infinity, if one of your bounds cannot be plugged in, we have to evaluate it using a limit instead. And since 0 is not part of the domain of z to the negative 1/3, to evaluate this, I will evaluate it by taking the limit as a goes to 0, and I can do it from the right because I only care about values bigger than 0, between 0 and 8. And I'll be the limit as from a up to 8 of z to the negative 1/3 dz. So like any other improper integral, if you ever have either a bound that's infinite or a bound that's just not part of the domain, you've got to replace it with either a on the bottom or b on the top and limit that value, that a or that b, to the appropriate number from the original integral bound. So let's see, I can do that. That's going to integrate, z is going to become z to the 2/3 when I add 1 to the power, multiplied by the inverse 3/2 from a to 8. And so I'll plug in the top. It's 3/2, 8 to the 2/3. Make sure that looks like 2/3. Minus, I'll do the limit as a goes to 0 from the right of 3/2 a to the 2/3. All right, we don't need to worry about this unless this converges, but it does, right? If a goes to 0, a to the 2/3, this is a continuous function, which means I could just use the just plug it in rule. Plug in 0 for a, and that gets me a big fat 0 there. So it converges to 0. Over here on the left, that's 3/2. The cube root of 8 is 2. 2 squared is 4. Cancel that, and that gets me a 6. So that limit does converge. That integral does converge. And we can see that up here in this picture, it may not look obvious, but this graph is getting so close to the y-axis that it basically cuts off any area, keeps it from growing infinitely large. It never gets any bigger than 6, in fact.